Hello, everyone. My name is Andrew Santangelo, and I'd like to share with all of you a little bit about CubeSats and SmallSats. And I'll be discussing today a little bit about the marketplace for CubeSats, their applications, how they operate, some of the systems on board a CubeSat, and what we're going to be using for our demonstration in our workshop today at the Cybersecurity Workshop at the AIAA Ascend 2020 event. Also, I'll be discussing some of the vulnerabilities that are similar to CubeSats as you would find in much larger satellites. CubeSats, as you can imagine, have a broad range of use, especially due to their size and lower costs. This range of use in applications and users has expanded substantially. Not only is there scientific missions and military operations, but the educational missions have expanded quite substantially to include not only universities and colleges, but also K through 12 missions. There's also, of course, commercial enterprise, not only with big space, but also with smaller entrepreneurial firms that now have a better entry into the satellite marketplace. And of course, civic operations and even hobbyists have gotten involved with CubeSats in small satellites. The marketplace for CubeSats and small satellites has actually been growing quite substantially over the recent couple of decades. As a matter of fact, they're projecting over 1,400 small CubeSats will be flown by 2022, along with mini satellite growth expected to go beyond 250 units per year. Now, when we talk about small satellites and cube satellites, it's a range of sizes going from pico satellites, which are under 1 kilogram, to all the way up to mini satellites, which can encompass satellites of up to 500 kilograms. But the uses are broad with small satellites and CubeSats, including scientific missions, meteorological missions, communications, research and development, and of course, intelligence gathering, to name a few. This, what you see here, is a very small sample of the CubeSat and SmallSat missions, just to give you a feel for what's going on here. For example, we have the Marco CubeSats, Auburn's Pride mission, which is flying in a couple of years, the Asteria mission, a range of NRL CubeSats, and very recently, Hawaii Space Flight Lab has sent up into the International Space Station where we deployed the Neutron 1 mission. On top of this, we have the Carthage College Canout mission, which is going early next year to study their rainforests. Now, I highlighted these last two missions because they're both flying the LinkStar D duplex radio systems and our LinkStar tracker radios for doing global communications and tracking. And these are the same systems we're going to be using for our demonstration here at the workshop. In the case on the Neutron 1 mission, you can see we have the LinkStar D radio and the antenna for the LinkStar D radio. And on the right, we have the duplex radio you can see nestled in a 3U CubeSat, in this case, the Canop mission. The components of CubeSat are very, very similar to much larger satellites. On the left, you can see the breakdown for, again, the Carthage College Canop mission, which includes the payload on the bottom, a multispectral camera to do imaging of the Earth's rainforest, but it does include also an onboard computer, as you imagine, electrical power system, EPS, batteries, uh, two other integrated computers, including a BeagleBone Black, the ADAC system, or Attitude Determination and Control System, including both the motherboard and the controllers themselves. And where you see the 1720, that is the radio system that they're going to be flying and which we're going to be using for our demonstration today at our workshop. Now, the Space Policy Directive 5 defines what a space system is. It includes three key elements: a ground segment, which includes operations and support, a link segment, our ground to space communications, and the space segment itself, the Earth orbiting satellites, planetary probes, and deep space satellites. Now, what you see here is not only holds for larger satellites in manned systems, but also applies to small satellites and CubeSats just the same. Now, for the workshop today, we're going to be using a similar setup with the LinkStar radio system and the QuickSat architecture. On this diagram here, kind of highlights what that system is and how it operates. On the left we have what would be the world of the satellite radio. In this case, we have the Flight Francis P. flight computer and the QuickSat vehicle management system, which is our flight management system and vehicle health monitoring for the satellite. That communicates to the LinkStar radio itself, which is the DCE, the GSP 1720. Now, there's actually two radios in our workshop demo today. There is a simplex radio, which you see kind of in the middle bottom there, which beacons over 95% of Earth orbit, both data and position information. And also the LinkStar duplex radio, which provides two-way communications to the satellite for about 40% of Earth orbit. And it actually treats the satellite as a node on the internet. Now, data from our LinkStar system on the small CubeSat set communicates to the Global Star satellite network, where you see satellite at the top there. And it communicates through a bent pipe fashion from the small satellite or CubeSat through the Global Star satellite network to the Global Star gateway or ground antennas. From there, Globalstar routes the data to our Amazon web-based service cloud, but also can route data, if people choose, to the AWS GovCloud or other cloud-based servers. And actually, for today's workshop, we're going to be using our own cloud-based servers located in the Albuquerque, New Mexico area. Now, from there, the data goes to the QuickSat vehicle management system or other server located at the operator station, ground station. And that can be the operator can use a laptop, a desktop computer, a range of desktop computers, or even mobile devices if they choose, like iPhones, Android phones, and graphic and tablets. So let's talk a little bit about the components of the LinkStar architecture that we're going to be using for the demonstration today. It starts with the computer, and there's actually two types of computers for our for the systems we're working with for this demonstration. One is Xilinx Zinc UltraScale MPSoC, which actually has been disabled for this demonstration, but also we're operating the a modified BeagleBone Black, which also runs the QuickSat system. Again, the QuickSat system does all the communications management, the vehicle health management, and actually operates the satellite. You can use it even on your CubeSat, use a Raspberry Pi in addition to a BeagleBone Black on the CubeSat. So you really don't need to go all in with a high-end Xilinx Zinc UltraScale NPSoC. From there, you have a range of radio options you can hook up to the satellite. For today's demonstration and workshop, we're using the LinkStar Tracker, which is a one-way beaconing radio providing global coverage, and the LinkStar D, which is a duplex radio providing two-way communication and treats the CubeSat as a node on the internet. Also, you can use a higher speed radio like the LinkStar HD, or even the S band, an X band radio, a Ka band, a range of radios. All these radios can be used at once on the LinkStar system with the QuickSat environment. Besides the radios and the computer itself, we have tied into this architecture for our demonstration today is a GPS, in this case, the OEM Novatel OEM 719. You can also use the Adafruit GPS for ground testing. It's a little bit of a cheaper option. And of course, you can have a range of sensors and actuators hooked up to your satellite, all communicating through the QuickSat environment through the radio systems. The QuickSat architecture is the brains of the satellite, and it will be used for today's demonstration. It starts with the StepSat DB flight database. This is the database that stores the flight data, tracks the commands, syslog, has the data models for the satellite itself, and of course various health monitoring information. To interface to the database when the satellite is on the ground for testing, you can use the QuickSat VMS web-based interface, which is very similar to the QuickSat VMS ground-based interface when the satellite is in orbit. So you can literally test like you fly, which is pretty cool. Now, to operate the satellite itself is the VMS vehicle management system and the VMS database interface that talks to the StepSat DB flight. You have a range of communication tools that brings allows you to upload new applications. You can upload commands and files to the satellite, and of course, transmit data up and down. Now, one module we're not going to be demonstrating today is the QuickSat Autonomy System, which provides AI and machine learning tools to the QuickSat environment, where you can be used for health, again, more advanced, sophisticated health monitoring, but also detects a range of cyber attacks on your CubeSat. One option that's provided in the QuickSat architecture we'll be seeing today is you can have custom commands added to your satellite without changing any of the code. And of course, add custom and add-on processes and even create what we call virtual payloads to the satellite. This provides a lot of flexibility, but you have to be mindful of the security of your CubeSat when you provide this level of flexibility. So CubeSats really are the Internet of Things in space. You can, for example, use it for tracking, hiking, mountain climbing, as you see in the upper left corner with the SpotX system talking to the Global Star Network. You can use it for border security, energy management, and monitoring, such as pipelines and windmills. You can also use it for firefighting, tracking, and for the security of the firefighters and looking at the expansion of a fire. And of course, there you can use it the LinkStar or CubeSats for radio communications for aircraft and UAVs. So think about Internet of Things in space with the LinkStar-QuickSAT example for today's workshop. You can have a satellite, a high-altitude balloon, a pipeline, a semi-truck, an oil rig, or even a sailboat communicate from the radio up to the Globalstar satellite network. From there, going bent pipe communications, it goes down to the Globalstar ground station. And then from there, Globalstar sends the data to our servers. Again, for this example today, they are located in the Albuquerque, New Mexico area. And from there, the customer mission control center or the operator can view the data on their laptop, desktop computer, or even mobile device. So as you can see, small satellites, just like much larger satellites, provide a range of flexible options and quite a bit of power and sophistication in application. But like any space system, they're vulnerable to cyber attack, such as in this example, the ROSAT X-ray attack that happened in 1998 is one example that happened to this satellite that can also happen to a CubeSat and small satellite. So if we think of our levels of operation on the ground, in 2005, for example, a rogue program penetrated the NASA KSC networks, which gathered data from computers at the vehicle assembly building and removed that data through covert channels. Thinking from a transmission point of view, Black Hat 2020 did eavesdropping on satellite ISPs. Basically, ISP not protecting their links, and it can be picked up quite easily. And of course, there's issues with the satellites themselves out in low Earth orbit, on the moon, or deep space, such as in 2008, the Terra EOS AM1 Landsat, there was an attempted satellite hijacking. So there's a range of vulnerabilities and issues as you would find not only with much larger satellites, but also small satellites and CubeSats that need to be considered.